Okay, section 14.3, we're going to look at partial derivatives. Here's an example. Suppose we have the heat index function. It's a function of temperature and relative humidity. At this point here, when the temperature is 96 degrees and the relative humidity is 70%, I ask the question, how does the heat index vary with respect to temperature at that point? So we're going to keep the relative humidity at 70%, and we're going to let the temperature vary. So you could say the rate of change then would be the change in the heat index over change in temperature. You could do that. It would be better to actually average this change here with from 125 to 133, which is what this is. Average it with the change from 118 to 125, which is what this is. And if you add those up and divide by 2, you get the rate of change of the heat index with respect to temperature at that point is 3.75. So that's the idea. Now, so we define the partial derivative of a function with respect to x. We're keeping y fixed at that point, and we're only letting x vary. And similarly, if you could define the partial with respect to y at that point by keeping x fixed and letting y vary. So here's an example. Here's my function. The partial with respect to x at 1, 2. I'm going to let x go from 1 to 1 plus h, and y is fixed at 2. So this is what we have. Now, what does that mean? You're plugging in 1 plus h here for x, and you're fixing y at 2. So you get this. And then here, this is just f of 1, 2. You divide by h and take the limit. Let's see, the 11s cancel. You can factor out the h, and you get 12. You could do the same thing with y. I'm going to let check that this is the partial with respect to y at that point. Hit the pause button there and check it yourself. All right, so we're not going to have to do that. We have a shortcut way to do it. When you have a partial with respect to x in general, we're keeping y fixed, and we're looking at we're treating y as a constant, and we're taking the derivative with respect to x. So here's an example. Suppose this is my function, and I want to know what is the partial derivative with respect to x. You're letting y fix. So in this first term, you see, think of y squared as a constant. So the y squared factors out, and you have 15x squared. Second term, the y squared is a constant, so you factor that out, and you take the derivative of 2x, you get 2. This, we're taking derivative with respect to x, so you get 6x, and the derivative of 11 is 0. So this is the partial with respect to x. So here's the partial with respect to y. I'm going to have you check that that's right. Hit the pause button and double check that, okay? Some notation. There's lots of ways to write it. F sub x, df dx. Notice we make kind of a fancy d there, but we say df dx. There's lots of ways to write it. F sub 1, I don't like that too much. I don't like this one either. But anyway, there's lots of ways to write the partial with respect to x. So let's do another one here. Here's my function, and I want to compute the partial of f with respect to x and the partial of f with respect to y. So we're treating y constant, right? So in this first term, the ln y factors out. It's a constant, and the derivative of x with respect to x is 1. Second term, it's a composition of functions, right? The 2 factors out. What's the derivative of tangent? It's secant squared of that function of x. But then you take the derivative of what's inside with respect to x. This is a constant times x, so you just pick up a y there. Anyway, I'll have you check that this is the partial with respect to y. So what is the geometric significance of this? Okay, well, if you've got a point AB, or you can think of it as AB0, and then this is your point on your surface, we're asking, this is your f of x, y, or z. When you look at the partial with respect to x, it's a better way to see it is over here. Let's take a look at this. Here's my function, and when you take the partial with respect to x, at this point 1, 1, think of it as you're fixing y at 1. So this is actually a plane. Y equals 1 is this plane that's perpendicular to the xy plane. Y is fixed at 1, so you're intersecting the surface with this plane. So really you're finding the slope of this tangent line. See how x varies here? So at this point, the slope of the tangent line turns out to be -2. This is the tangent line, which is the which is the tangent line to the curve of intersection with the surface and the plane y equals 1. Similarly, if you want to take the partial of y at 1, you're going to fix x at 1. So think about this is the intersection of this plane x equals 1 with the surface. And at this same point, we're letting y vary. And this is the slope of the tangent line to this curve of intersection there. See? Now notice this slope looks like this is -4 because as y varies, it's going down. This is -2 because as x increases, it's going down. So that's the geometric interpretation. You could find the second partial derivative with respect to x and y. Notice it gets more complicated here. You could take the partial with respect to x and then take the derivative of that with respect to x. That's called f sub xx. It gets a little tricky here if you take the partial with x and then the derivative of that with respect to y. It's written as f sub xy. So make sure you don't get the order mixed up. You first take the derivative with respect to x, and then you take the derivative with respect to y. But if you use this notation, you see here the dx is actually the inside one. So make sure you notice that. Here you take the partial with respect to x first and then y. It's written like this, but if you use this notation, it would be x then y. So make sure you understand that. All right, so here we go. I want to find all second partial derivatives of this function. So the derivative with respect to x, you fix y, so you get a y times 12x cubed, which is this, and then here you get -2 times y cubed, and here you get 5. Then you take the partial of that with respect to x, the partial of this with respect to x. That just gives you the partial of this with respect to x. You factor out the y, and you get you factor out the 12y, and you get 3x squared, which is this. Now notice, the derivative of this with respect to x is 0. The derivative of this with respect to x is 0, and so is that. So you only get one term. Now I can also go back here and take the partial of this with respect to y. So x is constant. So the 12x cubed factors out, and you get a 1, which is this term. And then you get minus 6x squared, which is this term. Now you could do this too. I'll let you hit the pause button. What you do see is you notice that these are equal. Z sub xy equals z sub yx, and that's what Clairaut's theorem says. It says if your functions are continuous, if the second partials are continuous, then the mixed partials are equal. That's nice to know. Let's do a couple more things here. Here's this is a surface, and we want to know. It's kind of hard to see this. This is the point 1, 2. This is actually the point -1, 2. We want to know from the picture of the surface, what is the sign of the partial with respect to x at this point. So remember, x is increasing. So you notice you're on this curve here, and as x gets larger, this curve is going up. So the partial with respect to x would be positive. Now, if you look at the partial with respect to y, you're on this curve here. Notice if y increases, the graph is going down in this way, so that's why it's negative. Now, if you want to look at the second partial at this point, I'm at this point now. As x increases, you see how the graph is concave up. This curve right here is concave up here. So since it's concave up, if you move in the x direction, that curve is concave up. So the second partial would be positive. And if you move along this curve in the y direction, it's not that it's decreasing, it's that it's concave down. That's why the second partial would be negative there. Keep on going. All right, so let's look at some more examples, all right? I'll do a couple, and then I'll let you take pictures of the rest. Let's look at this function. We want to find the partial with respect to x, and the partial, it should be t. I said y, shouldn't that be t? Yeah, it should be t. Okay. Anyway, here we go. What's the partial with respect to x? This is to the 1/2 power. It's a function of the 1/2 power. So you get 1/2 times this function to the negative 1/2 times the derivative of what's inside with respect to x. So that just gives you a 3 there. What's the partial with respect to t? It starts out the same, right? It's 1/2 this thing to the negative 1/2. But when you take the derivative of what's inside with respect to t, you get a 4. So that would be the partial with respect to t. Let me do one more, then I'll have you do the rest. Okay, let's do 22. So I want to look at the partial with respect to x. So this is a quotient rule, right? It's the bottom times the derivative of the top minus the top times the derivative of the bottom. Now when you take the derivative of what's inside, you get 1 over the bottom squared. So that simplifies to this. If you go back and look at this as a function of y now, actually as a function of y, you don't have a quotient rule. X is a constant, right? So it's just x times this thing to the negative 2 power. And so you would get negative 2 times this thing to negative 3 times what's inside. Notice you don't have to use the quotient rule because it's not the quotient of two functions of y. All right, I'll let you, you 24 and 25, hit the pause button. You can check those. Let's see, find the indicated partial. Let's do a couple of these. Look at number 44. So I want you to find the partial with respect to z. By the way, this is a function of 3 variables, right? The partial with respect to z at the point e10. So you would, now by the way, this function, if you're looking at x and y as constant, it's basically a constant to a constant times z, right? So if you want to take the derivative with respect to z, if a and b were constants, it'd be ln of a times b to the z times b. I'm just in general, okay? So that's how we're looking at it. The derivative of this with respect to z would be ln of x times x to the yz times the derivative of what's inside with respect to z, which is y. And when you plug in e equal 1, x equal e, y equal 1, and z equals 0, you get 1. I'll let you, let's do one more here. What about this? It says find the partial with respect to z, partial with respect to x and partial with respect to y of this one right here. I'll let you do that one. Just check these, okay? Try this one on your own. Go ahead and hit the pause button. Okay, we're almost done. Let's do one more here. It says find all the second partials for number 54. So it would be you have to find f sub x first and f sub y. So the derivative with respect to x would be 1 over this thing times a, and the derivative with respect to y would be 1 over this thing times b. And then you would take the derivative of that with respect to x. So the a factors out, and you get, this is ax plus by to the negative 1 power. So you get negative this to the negative 2 times the derivative of what's inside. And you get this. Anyway, you can do the same thing with the partials with respect to y. You would take take the derivative of this with respect to y. So you would get, this is b times this thing to the negative 1 power. So you would get, b times negative this thing to the negative 2 times the derivative of what's inside. That's where you get your b squared. And the mixed partials are going to be equal. That's what Clairaut's theorem says. If you take the derivative with respect to x and not take it with respect to y, the derivative of this with respect to y, it's going to be a, this is to the negative 1 power, so it's ax plus by to the negative 2 times the derivative of what's inside, which would be b, so you get this. And if you were to first take this and then take the derivative of this with respect to x, you get the same thing. Okay, so hit the pause button, you can check this out. And I guess that's just about it. Talk to you later. Bye-bye.